Hello, everyone. I'm Lulu Yu from Institute of Computing Technology, Chinese Academy of Sciences. It's my pleasure to be here to report our winning solution for Wisdom Cup. This is a joint work with Yiting Wang, Xiaoyue Sun, and two other teachers. Firstly, I will introduce the background. Ranking model has been playing an essential role in reward systems, especially search engines. It typically aims to learn scoring function based on the human annotated relevance labels. Since user clicks on document indicate users' implicit feedback on the document's relevance, and it is cheap to collect a large scale of them. A common practice in search engines is to train a ranking model with the feedback data. Although user feedback data is easy to obtain, they contain a lot of noise and biases, such as position bias, selection bias, and trust bias. Thus, optimizing the model directly with such signals could lead to unsatisfied performance. Based on the search logs of the largest Chinese search engine Baidu, the Wisdom Cup presents the tasks of unbiased learn to rank and pre-training for web search, requiring participants to learn an unbiased ranker and obtain an effective pre-trained model from user feedback. The second part, device pre-training. We firstly pre-process the data and extract the representative features. There are around 1.2 billion query document pairs in 2,000 partitions in this competition, which are extremely large, and it will take a long training time and large computation costs to train on the whole dataset. Due to the limitation of our computing resources, we only use one party to train the model, and leave the research of training on larger data with our strategy for the future. Besides, we discard queries without clicks on the whole candidate list and filter out the queries whose candidate documents are fewer than 10. In order to enhance the representation ability of the ranking model, we extract well-known features such as BM25 and query likelihood with different smoothing methods for multiple document fields. Our model has a wide and deep architecture. It learns semantic matching using deep neural networks and incorporates exact matching features with a shallow network. Specifically, on the left is the deep network. We adopt the well-known cross-encoder composed of multi-layer transformers to encode the concatenated query and document text. CRS token embedding is regarded as an input vector, representing semantic matching. In the wide network on the right, we project the features to hidden vectors, concatenate them with the embedding of CRS, and finally feed them to a linear layer to obtain the relevant score. We find that training an end-to-end ranker based on the pre-trained model and the click data, whether with or without unbiased learning, cannot outperform heuristic-based features such as BM25. So we design a level refinement strategy by incorporating the best feature with the clicks according to Figure 2. The main idea is that given a list of candidate documents for a query, the scores of clicked documents need to be higher than non-clicked documents. On the basis of maintaining the feature order of clicked documents. Based on the refined label, we perform the list-wise loss function to train our model. Since the documents displayed to the user already have different degrees of relevance, in order to make the model see more negative samples, we randomly add a specified number of random negative samples to the list and set their labels to 0. And considering the documents after the last click may not actually be observed by the user, we replace these documents with random negative samples to alleviate the false negative problem. According to the organizer's paper, the dual learning algorithm performs best. Thus, we first choose DLA as our training strategy. Surprisingly, we found that the learn propensities are not decreasing with respect to positions. The reason may be that the click data of real-world search engines contains not only position bias, but also presentation bias, invalid clicks, and so on. The learning process of propensity value may be impaired owing to the above mixed factors. What's more, we refine labels by combining the clicks and the exact matching signals, which makes the situation even more different. In order to ensure the stability of the learning process for biased data, we calculated the click ratio on different ranking positions to estimate the reasonable inverse propensity weights. As shown in the formula, we multiply the static inverse propensity weight by the original list-wise loss function. We train the transformer with 3 and 12 layers, combined with 10 and 20 negative documents, used different values of batch size, and tried the training strategy of dual learning algorithm and the fixed propensity. After linear combination, we got the final score of the above ranking models. The third part, in addition to the above-mentioned unbiased pre-training methods, shared by the two tasks, we will introduce the specific part of Task 2. The solution of Task 2 has 2 stages. In the first stage, in addition to the parts already introduced, we use the human annotation dataset to fine-tune. In the second stage, taking the extracted features and the output scores of previous pre-trained and fine-tuned models as input, we train a gradient boosting decision tree model to Ensemble. Here are the 3 strategies for fine-tuning in total. The first is the ranking loss. A simple way to deal with multi-level relevance labels is to transform them into positive and negative classes using a pointwise loss function. But the ranking task does not pursue accurate scoring, and relative scoring is accessible. Therefore, a pairwise method for modeling the relative relationship between positive and negative samples is needed. We further introduce a certain number of negative samples into the pairwise loss function formula, so that the model can better improve the relative score of positive samples. And because the labels in this dataset are multi-level, if a document is marked as perfect, excellent, or good, then the document is a positive sample. Otherwise, the document is a negative sample. The second strategy is sample augmentation. Unlike clicked data in the search log, the cost of manual labeling is high. Therefore, it is promising to enhance the effect of core samples in the fine-tuning stage. We find that high-frequency queries have more positive documents, so we consider these queries as a core and conduct more training on these queries to let the model learn common matching patterns. Finally, as mentioned earlier, we train a gradient boosting decision tree model using LightGBM in the validation side with lambda rank objective. All our code is based on paddle, and we use the official model for initialization. In the fine-tuning stage, we divided the expert annotation set into 2 parts, training and validation. Then we select the best model based on the performance of the validation set. The last part is the result and conclusion. In summary, we use the transformer model as the backbone, with a combination of inverse propensity weights, negative sample augmentation, and label refinement in the pre-training. A pairwise ranking loss, core sample augmentation, and the ensemble strategy are used in the fine-tuning. Our solution won the 3rd place both in Task 1 and Task 2. That's all of our report. Thanks for listening.